Steel and cast iron look almost the same at first glance. Both are based on iron. Both are used in machinery, construction, automotive engineering, and energy systems. And yet their mechanical behavior, reliability, and applications are fundamentally different. Confusing steel with cast iron in a real engineering design can lead to cracked parts, sudden failure, or catastrophic structural damage. The key question is simple, but the answer is deep. How can a small difference in composition create such radically different materials? The first thing that must be made absolutely clear is this: neither steel nor cast iron is pure iron. Both are iron-carbon alloys, and it is precisely the amount of carbon and the way it behaves inside the metal that determines everything: strength, ductility, brittleness, machinability, and even how the material must be manufactured. If you like similar educational videos, please like, subscribe, and share the video with your friends. The difference between steel and cast iron is not about quality. One is not better than the other. The difference is what kind of mechanical stress each material is designed to handle. Steel excels under tension and bending. Cast iron excels under compression and vibration damping. That single distinction already explains why they are used in completely different places. To truly understand this, we must go deeper than surface properties. We must go down to the atomic level. We must understand how carbon interacts with iron, how the metal solidifies, and why two alloys made from the same elements can behave in opposite ways when loaded. The differences begin already during production. Steel and cast iron are melted, solidified, cast, and processed in very different ways. What is an advantage for steel often becomes a limitation for cast iron and vice versa. A practical example makes this obvious. Crankshafts are almost always made of steel. Engine blocks are very often made of cast iron. Not because one is cheaper, but because each material is perfectly suited to a different type of stress and function. The fundamental difference between steel and cast iron begins with carbon content, but it does not end with a number in a table. What truly matters is how carbon behaves inside iron and how it reshapes the internal structure of the material. Steel contains a relatively low amount of carbon. Because of this, carbon atoms can remain dissolved within the crystal lattice of iron or form very fine internal structures. The result is a material that stays continuous, coherent, and mechanically cooperative. Carbon strengthens steel, but it does not break its internal connectivity. This is why steel can be stretched, bent, forged, rolled, and welded. When steel is loaded, stress can spread across the material instead of concentrating in one place. The structure works together as a whole. Cast iron, by contrast, contains significantly more carbon. At this point, iron can no longer keep all the carbon dissolved. The excess carbon must separate out. It forms graphite or hard iron carbides, depending on how the alloy solidifies and what additional elements are present. This separation is the turning point. In cast iron, carbon does not reinforce the structure. It interrupts it. From a mechanical perspective, graphite particles behave like internal discontinuities. They divide the metal into regions instead of binding it together. Under stress, these regions become preferred locations for crack initiation. This is why cast iron reacts so differently to load. Steel distributes stress. Cast iron concentrates stress. Alloying elements play very different roles in each material. In steel, elements such as chromium, nickel, manganese, or molybdenum are used mainly to increase strength, toughness, corrosion resistance, or hardenability. In cast iron, those same elements are often used to control the shape and distribution of carbon rather than to directly increase strength. The shape of carbon matters enormously. Thin graphite flakes create strong stress concentrations and make cast iron very brittle. Rounded graphite particles reduce stress concentration and dramatically improve toughness. The material is still cast iron, but its behavior changes radically. This leads to an important realization. The difference between steel and cast iron is not just how much carbon they contain, but how carbon is allowed to exist inside the metal. From a chemical point of view, steel uses carbon as a strengthening tool. cast iron must accommodate carbon as a structural feature. That single distinction explains most of the mechanical behavior engineers observe in practice. The true reason steel and cast iron behave so differently becomes clear only when we look inside the material itself. Not at composition on paper, but at microstructure, the internal arrangement of phases, carbon, and crystal boundaries. This hidden structure determines whether a material absorbs energy or releases it catastrophically. In steel, carbon is either dissolved in the iron lattice or present in extremely fine, well-distributed phases. The internal structure is continuous. When steel is subjected to tensile or bending stress, its crystal lattice can gradually rearrange. Dislocations move. Stress is redistributed. The material begins to deform plastically instead of breaking. This behavior is critical in real-world applications. Steel does not fail silently. Before fracture, it stretches, bends, or necks. Engineers can see deformation. Machines give warning. Structures buy time. This is what we call ductility and toughness. In cast iron, the situation is fundamentally different. Excess carbon forms graphite or carbides that break the continuity of the metal. From a mechanical standpoint, these features act like microscopic cracks already embedded in the structure. When cast iron is loaded in tension or bending, stress cannot spread smoothly. It concentrates at the edges of graphite particles. Once a critical stress level is reached, a crack forms and propagates extremely fast. There is almost no plastic deformation. Failure is sudden and brittle. This does not mean cast iron is weak. Quite the opposite. Cast iron has exceptionally high compressive strength. When loaded in compression, those internal graphite structures are not dangerous. They are largely irrelevant. This is why cast iron performs so well in massive, stationary components. Another key advantage of cast iron lies in vibration damping. Graphite acts as an internal energy absorber. Vibrations are dissipated instead of transmitted. Steel, by comparison, tends to pass vibrations along the structure. In precision machinery, this difference is enormous. Not all cast iron behaves the same way. If graphite forms as sharp flakes, brittleness is extreme. If graphite forms as rounded nodules, stress concentration is greatly reduced. The material remains cast iron, but its toughness improves dramatically. This shows how microstructure can dominate behavior, even when chemical composition changes only slightly. To summarize this section, steel absorbs energy through deformation. Cast iron absorbs energy through mass, and damping steel gives warning before failure. Cast iron fractures abruptly. Once the differences in composition and microstructure are clear, the practical logic becomes obvious. Steel and cast iron are not interchangeable materials. Each one is optimized for a completely different role, and using the wrong one in the wrong place is not a minor mistake. It is a design failure. Steel is chosen wherever a component must carry tensile loads, bending, cyclic stress, or impact. These are situations where forces change direction, where overloads are possible, and where failure must never occur suddenly. Steel is ideal because it is ductile, tough, and capable of absorbing large amounts of energy before breaking. That is why steel is used for shafts, axles, and rotating parts, structural frames, bridges, and load-bearing beams, bolts, fasteners, springs, and safety-critical components. Parts exposed to fatigue and repeated stress cycles. Steel can also be forged, rolled, welded, and heat-treated with great precision. Engineers can tune its properties to match a specific application. This makes steel a highly adaptable material for dynamic systems. Cast iron, on the other hand, excels in a completely different environment. It is used where compressive loads dominate, where dimensional stability matters, and where vibration and noise must be suppressed. Cast iron does not like to flex, but it is extremely good at staying exactly where it is. Typical cast iron applications include engine blocks and cylinder liners, machine tool beds and frames, pump housings and valve bodies, gearbox casings and brake components, heavy infrastructure elements. One of cast iron's greatest advantages is castability. It flows easily into complex molds, allowing large, rigid parts to be produced in a single piece. Combined with excellent vibration damping, This makes cast iron ideal for massive, stationary components. There is also a crucial difference in joining and repair. Steel can be welded and repaired relatively easily. Cast iron usually cannot. Welding cast iron requires special procedures, and in many cases, replacement is the only realistic option. This is why cast iron is typically used in components designed to remain static and intact for their entire service life. Modern engineering often combines both materials in one system. Steel components handle forces and motion. Cast iron provides stability, rigidity, and damping. A classic example is an internal combustion engine, steel crankshafts and connecting rods operating inside a cast iron block. And this leads to the most important conclusion of the entire video. Steel and cast iron are not competitors. They are tools. Each one exists to solve a different mechanical problem. If you need a material that bends, stretches, and warns before failure, you choose steel. If you need a material that holds shape, absorbs vibration, and carries compressive loads, you choose cast iron. Confusing the two is not just a material error. It is a misunderstanding of how matter behaves under stress. And that is the real difference between steel and cast iron.